Before we jump back into Amy's house pricing, let's talk about a few bits of machine learning vocabulary. First of all, parameters. If we're talking about linear regression, you know what the parameters of your fitted model are. They are the coefficients. But how did you personally control the coefficients? How did you decide if they were big, if they were small, if you're going to have a complicated model or a simple model? Well, you chose lambda. A parameter which controls your parameters is called a hyperparameter. We've looked so far at two different methods for penalization, L1 and L2. We found that both L1 and L2 allowed us to vary the complexity of the models, but L1 in addition also allowed us to vary the interpretability of a model. If we used L1, parameters simply dropped out completely when they weren't very important, and we had models with a relatively small number of non-zero coefficients. You can think, therefore, of lambda itself as controlling the complexity of the model, and whether or not you choose L1 or L2 as controlling to some extent the interpretability of the model. Wouldn't it be amazing if there was some way of sliding between L1 and L2 according to how much interpretability you wanted? And that's on the assumption that we might lose some performance as we move towards L1, so we want some way of choosing between performance and interpretability. Well, there's something called elastic net, which has a parameter alpha, and that alpha allows us to choose between L1 and L2. From memory, when alpha equals 0, you'll get L2. When alpha equals 1, you'll get L1, and if it's in between, you'll get a linear combination in between. Alpha is therefore also a hyperparameter. When we move on to decision trees, the depth might be a hyperparameter. When we move on to gradient boosting, the step size will be a hyperparameter, and so on. There are loads of hyperparameters. So the question is now, given that we have these hyperparameters, how do we tune the hyperparameters to give us the best performance given any other constraints that we have with our models, such as a required interpretability? Well, the starting point for all machine learning is that out of all your data, you set aside a certain amount of the data for testing your final model. That's assuming you actually want to know whether your final model is any good whatsoever on data that it has never seen before in any way whatsoever. And I hope we can agree that it is important to know whether your model is good on the kind of data it's going to be used for, i.e. data it's never seen before. But out of the data that we do have to build our model, how are we going to use it to fit the model and choose the hyperparameters? Now, let's go back to our first hyperparameter, lambda. That was to help us avoid overfitting. We can't fit lambda on the same data that we use to train the model because we won't know if there's any overfitting or not. The only way we know whether or not there's overfitting is to measure performance, again, on data the model has never seen, and to see when that performance starts deteriorating as model complexity increases. The only way to do this, seemingly, is to split the data that we do use for training the model between trained data and validation data. That's exactly what we did when we were tuning our lambda. We tried lots of different values of lambda on the trained data, and each time we tried them, we tested the performance on the validation data, and we looked for the best performance, which was typically somewhere in the middle. That concept of splitting the data between trained data and validation is called, unsurprisingly, cross-validation. Well, I say unsurprisingly cross-validation. I suppose I would have just called it validation, because that's what we're doing. We're validating the performance on data the model has never seen. Well, for whatever reason, it's called cross-validation. Now, the third time I'm saying this sentence, for one reason or another, the thing about validation is you might not have very much data in your validation data set. Don't forget, you might not have had very much data at all. In Amy's housing, we only had 2,900 houses. We must set aside some for test, and the remainder has to be split between train and validation. Now that's a problem, because that means that when you estimate the performance on your validation data set, there's going to be a certain degree of noisiness in that, and this best parameter that you fit might have been different if you would have looked at a different subset of your data. What's the answer to that? The answer to that is simple. We have our original data set, if you remember, of which we set some aside for test, which we can never use. What we'll do now is, of the remaining data, we'll take some of it for train and some of it for validation. And on the basis of that, we will draw our validation curve. If you remember, on the x-axis we had complexity of model, which was in fact controlled by lambda. On the y-axis we had the loss function. Now we're saying that this particular curve that we've drawn might be to a certain degree volatile and random depending on the validation dataset that we chose. So what we'll do now is we'll simply repeat the process, this time using this data here, plus the data we previously used for validation as our train data, and we'll use a different bit of data for validation, and no doubt we'll get a slightly different curve. And we can do that again, and again, and again. If we do that process 10 times, for example, we'll have 10 different cross-validation curves, all of which are slightly similar. And what we can do is we can take the average of those curves. Now, what is true about the average of those curves? Well, one thing that is true is that it's been fitted using all of the data. We repeated the process enough times so that each part of the data was used for validation once. Well, what is true about this average curve? Firstly, it's likely to be much less volatile than the individual curves. It's likely to be much more accurate than the individual curves. You can see in this particular case that the optimal lambda varied from here all the way down to here, maybe. So there was definitely volatility in each of the cross-validation samples, but hopefully overall taking the average will give us a better estimate. What have we talked about so far? Parameters, hyperparameters, cross-validation, and the thing that we just did, where we took all of the data we were interested in, excluding the test, and then we split it into different pieces, and we repeated cross-validation a certain number of times, each time using a different piece for the validation. That is called k-fold cross-validation, because we split the data we're going to use for modeling into k-folds, and each time we do cross-validation we use a different fold. Most frequently you'll find people doing 10-fold cross-validation. What's the most extreme version of this? Well, imagine you have, say, 10,000 observations, and you split your data into 10,000 folds. That means each time you're doing cross-validation, each time you're doing k-fold cross-validation, you're just leaving out one observation, and in the end you would take an average of 10,000 validation curves. The idea of leave out one cross-validation is unsurprisingly referred to as LOOCV, and you might think that's ridiculous, but there is at least one situation where I've seen it used, and that is in the R package for generalized additive models, where it's possible to do this in an analytical way. I think that's it. That's all I wanted to say about parameters, hyperparameters, cross-validation, and k-fold cross-validation. We're going to see that in practice very shortly.